Hey, what's up, Chem Peeps? Who's ready for some more free response? I know there is nothing I would rather be doing except this. A solution of 0.10 molar nitric acid is prepared to determine the concentration of 20.0 milliliters of a potassium hydroxide solution. The 20.0 milliliters of potassium hydroxide solution is placed in an Erlenmeyer flask. A pH probe is used to obtain pH readings throughout the titration experiment. To reach the equivalence point, 30.0 milliliters of nitric acid is added to the Erlenmeyer flask. Part A. Write the balanced molecular equation for the reaction between nitric acid and potassium hydroxide. Oh yes! Get to show off my chemistry skills. Nitric acid, boom, HNO3, reacts with potassium hydroxide, boom, to form water and a salt. In this case, potassium nitrate. Once again, if it hasn't made it through your skull yet, nomenclature is super important. Like, way more important than anything you will ever do in English class. And of course, once you've got the nomenclature right, go back and double check. Make sure that the equation as written is balanced. In this case, I'm doing a little dance. Because it already is. Subpart I. Write the balanced net ionic equation for the reaction between nitric acid and potassium hydroxide. Oh yeah, nitric acid, one of my strong acids, is going to completely ionize into hydrogen ion and nitrate ion. Potassium hydroxide going to completely ionize into potassium ion and hydroxide ion. Water is a liquid. That sucker is going to stay together as H2O. And then potassium nitrate, a highly soluble salt, is going to ionize into potassium ions and nitrate ions. As I take a look at both sides of the equation, I'm going to cancel out things that are spectating, that are aqueous on both sides of the equation. Goodbye nitrate, adios potassium. Which means that my net ionic equation, boom, focuses on the things that come together to form water. It's important to recognize that this net ionic equation is the net ionic equation for all strong acid and strong base reactions. Part B. Using the information provided above. Subpart I. Calculate the number of moles of potassium hydroxide that were in the 20.0 milliliter sample. Alright, I'm looking for moles of potassium hydroxide, but as I come back up here, all I know about potassium hydroxide is that it was in 20 milliliters. That's it. I'm not given any other information about the potassium hydroxide. Oh, but I do know that I titrated it with 0.10 molar nitric acid, and it took 30 mils of the nitric acid to reach the equivalence point. So say hello again to my good friend molarity. Boom. I know the concentration is 0.10 molar, and I know that it took 30 milliliters or 0.0300 liters to reach the equivalence point. Jump to your calculator. My number of moles of nitric acid, 0.0030 moles nitric acid. Alright, feeling great, but it wants moles of potassium hydroxide. So, I'm going to utilize my balanced chemical equation that I just wrote up here in part A, and note the relationship between nitric acid and potassium hydroxide is 1:1. Set up my dimensional analysis. Boom. That relationship of 1:1 between nitric acid and potassium hydroxide coming from that beautiful balanced chemical equation that I just wrote up in part A. Boom. No calculator required. I know then my moles of potassium hydroxide, 0.0030 moles. Boom. Take a moment, look at the work that I've done. You want to be able to not only tell me what your answer is, but show me how you got there. So you want to be comfortable using the molarity equation and your dimensional analysis. Subpart II. Calculate the concentration of the initial potassium hydroxide solution. Once again, molarity. Boom. 0.0030 moles potassium hydroxide. Head back up to the information provided in the question prompt and recall that that number of moles was originally in 20.0 milliliters. Or 0.0200 liters. Quick jump to my calculator. The original concentration of the potassium hydroxide solution, 0.15 molar. Boom. Subpart III. Show a numerical setup and calculate the pH of the initial potassium hydroxide solution. Well, let's take a look at the work we just completed in earlier parts of the problem. we determined the original concentration of the potassium hydroxide to be 0.15 molar. And because I know that potassium hydroxide is a strong base and that the ratio between potassium hydroxide and hydroxide is 1:1, I also know that the concentration of the hydroxide ion is 0.15 molar. So even though I'm looking for pH, I'm going to start off with POH. Again, because the solution I'm working with is a potassium hydroxide solution. Keep in mind, formula for POH is equal to the negative log of the hydroxide ion concentration. And as we just determined, that concentration is 0.15 molar. Quick trip to the calculator. Negative log, second answer. My pH of this potassium hydroxide solution, 0.82. Then keep in mind the following relationship between POH and pH. They sum together to equal 14. So if I know the POH is 0.82 and the pH is what I'm looking for, all I have to do is subtract my POH from 14. So the pH of my solution, initially 13.18. Boom. Now stop and think, does it make sense that a potassium hydroxide solution, a basic solution, a base, would have a pH greater than 7? Heck yeah, it does! Bases have pH greater than 7. Which brings us finally to part C. When the student has added 60.0 milliliters of the nitric acid to the Erlenmeyer flask, the pH is determined to be 1.43. On the axis below, subpart I, plot the points at which 0.00 milliliters, 30.0 milliliters, and 60.0 milliliters of titrant have been added to the Erlenmeyer flask and sketch the general shape of the titration curve. Alright, we got this. Initially, we were working with the potassium hydroxide solution, and we just determined in part B, subpart I, that the pH of our initial solution was 13.18. Boom! I've plotted the point at 0.00 milliliters. Now remember, the next point I have to plot is 30.0 milliliters. And if you've forgotten, head back up and recall that 30 milliliters is the volume of nitric acid that I had to add to reach my equivalence point, or the point at which we've got stoichiometric amounts of our acid and base. And because the acid and base are both strong, at the equivalence point, the pH is gonna be 7. Boom. 30 mils, pH 7. And then, easy enough, we're told that at the 60 mil mark, our pH is 1.43. Boom. Now, here's where your knowledge and experience of titrations is gonna come into play. It might be tempting to just draw a straight line, but keep in mind that the pH stays pretty constant until we get to our equivalence point, where we see the big drop, and then it levels out again. So again, we're just asked to sketch the general shape of the titration curve, so make sure you've got a steep inflection at your equivalence point. That does it for this vid. Have a fantastic day. I know after watching that vid, I sure will.